Morning, afternoon, or evening, anyone that's listening to this episode. Welcome to another revision session with Seneca. Today we're going to be going over reaction profiles. This is the second episode looking at reaction profiles, so make sure you check out the first one. Today we're just going to be delving into a little bit more depth and talking specifically about catalysts and the way they interact with reaction profiles. So catalysts are really important because they can increase the rate of a reaction, and they do this by lowering the activation energy. And whenever we're talking about reactions and energy, we think about collisions. Molecules collide, and if that collision is successful, it means that the reaction can occur. So by lowering the activation energy, it means that there are more successful collisions. So what was the type of energy that catalysts reduce? It's the activation energy. And the activation energy is the minimum amount of energy required for a reaction to start. And if we look at an energy or reaction profile, we will see that when a catalyst is added, the size of the line between the reactants and products is less. And that is because the catalyst lowers the activation energy. Okay? So if we're talking about collisions and reactions, we need to talk about chemical bonds, because all chemical bonds have a bond energy, and that's basically just a measure of the strength of the bond. And what we can do is, if we subtract the total bond energies of the products from the reactants, we can tell whether a reaction is exothermic or endothermic. If you're not sure on those terms, I'll quickly review them, but there is a separate podcast on exothermic and endothermic reactions, so give that a listen. And endothermic reactions, they take energy in from the surroundings, and basically the energy released by making bonds is less than the energy required to break the bonds. Whereas with exothermic reactions, the energy released by making bonds is greater than the energy required to break the bonds. So energy is given out to the surroundings, normally in the form of heat. So exothermic reactions normally cause an increase in temperature of the surroundings. So to summarize, bond breaking is an endothermic process, and bond making is an exothermic process. Really, really important. And a reaction is exothermic if less, is endothermic if the total energy released by forming the bonds is less than the total energy required to break the bonds. Cool. Okay, so just to recap what it looks like on an energy profile or a reaction profile, when we have a catalyst present, we have a lower activation energy, so the line looks lower, but the energy of the reactants and products stays the same, and the enthalpy change of reaction, or delta H, that's going to remain the same as well. Okay, so let's subsequently review the calculations that can be associated with bond energies. Now, as I mentioned before, it's always the reactant bond energies subtracted from the product bond energies, okay? So the total energy change of a reaction, we add up all the reactant bond energies and we subtract all the product bond energies. So let's go through an example. If we have the reaction that makes water, we have gaseous hydrogen and oxygen, which comes together to make water. So the symbol equation would be 2H2 plus O2 goes to 2H2O. It's really important to draw the symbol equation because you need to know how many of each molecule there are. If we look at the reactants, we've got two H to H bonds, and they have an energy of 432 kilojoules per mole, and one oxygen to oxygen bond, and they have 142 kilojoules per mole of energy. So if we want to calculate the reactant bond energies, we do 2 times 432 plus 142. Okay, that's the first step of our calculation. Do you remember what we need to do next? Next, we need to subtract the product bond energies. So in our products, we have 2H2O, which is 4 OH bonds. Each OH bond has 459 kilojoules per mole of energy. So from our first number, we subtract 4 times 4, 5, 9. And if we subtract them, we get minus 830 kilojoules per mole. Now the minus sign means that the reaction is exothermic, whereas a positive sign means the reaction is endothermic. So do we remember what catalysts do? They decrease the activation energy. And if the total energy released by forming bonds is more than the total energy required to break bonds, what kind of reaction do we have? Exothermic. Okay, so that completes reaction profiles. Hope this was useful. Let me know what you thought, and I'll catch you on the next episode. I've been Jono from Seneca. Cheers.